All right, video 12 and counting down. You really are getting close. Hang in there. I know you'll really appreciate this when we do the application in class. We're on video 12 and we're going to look at another mathematical tool for calculating the molar mass. And this time we're going to be using colligative properties. Specifically, the only two we're going to look at right now. There's more, and we'll deal with those later on in the semester, probably next semester actually. But for now, just for the sake of the boiling point or the molar mass, we're going to be doing boiling point elevation and freezing point depression. Now, a colligative property, that's what these are called, colligative properties. I wonder if that's only got one L, but hopefully you'll forgive my spelling. So colligative properties depend only on the amount of solute. So what our goal is to find moles of solute. Now, if we have a covalent molecule, for every 1 mole of solid solute that goes into solution, so if that's 1 mole there, we're going to get 1 mole of aqueous. So instead of dealing with different formulas, I like to use one formula. We're going to see in just a minute. And so I say that I is 1. If I call I the number of particles, that's a little simplistic, but it'll work for what we're dealing with right now. So if it's a covalent molecule, you may see the words instead of covalent molecule, you may see non-ionizing. It means it does not break up into ions because of course it's covalently bonded. Or non-electrolyte. That means it does not conduct electricity in solution. In order to conduct electricity, you need ions. If it's covalent, you don't get ions. And so you'll see some other words that will give you an indication that N is equal to 1. Now, if the solute simply has carbons, hydrogens, maybe oxygens, we know we're dealing with organic. And when we're dealing with organic, we're talking about molecules. And so that word organic, or seeing all carbons, hydrogens, oxygens, maybe a nitrogen here or there, that would mean that I is equal to 1. Now, if it's a soluble ionic, it breaks up into ions. And so we don't want just moles of solute, we need moles of ions. And we're ultimately going to deal with that by determining how many particles we get, how many ions we get. So for example, if we took aluminum sulfate in solution, aluminum sulfate, when it goes into water, is going to break into 2 aluminum ions plus 3 sulfate ions. So if I counted those ions, I would get a value of I is equal to 5. Now, again, it's called the Van Hoff factor. It's a little bit simplified view. Sometimes experiment will show us that it's not exactly 5, but unless you're told otherwise, this is what we'll be using when we deal with our colligative properties. Now, I like to kind of build up my formulas for this. So let's take a look at the next slide and build up the idea of this. Now, if I have a pure solvent, and here's its boiling point, if you add a solute, you will always get an increase in boiling point. That's precisely why we add salt to our water, because it will increase the boiling point, which means our spaghetti is cooking at a higher temperature, which means that the spaghetti will cook faster. Now, it will take a little bit extra time to boil, but that will be made up in the speed of boiling. And of course, salt also tastes good, so it helps our flavor. So if you notice, as we go from the boiling point of the solvent to the boiling point of our solution, we have a change in boiling point. Now, what we're going to build up are the formulas that we use for this, and we're going to see that the boiling point, notice it's an elevation, it goes up. The formulas mirror one another. So the simple formula for this is molality times a constant that tells us about the structure and function of the solvent. That would typically be given, or maybe possibly an unknown, but you're not expected to memorize those. Now remember, we need particles. So if I multiply by I, I'll get molality of particles, not simply molality of the solute. Now, I like to use the expanded form sometimes if you're given molality or asked for molality. So if you're going in and out of molality, I would pick the simple form. But we're dealing primarily right now with molar mass. So to do the molar mass instead of molality, I'm going to put mass over molar mass. That's my moles, remember. I told you that'd be a handy formula. Divided by kilograms of solvent. And that would be my molality factor. And then we still have our Kb and our I factor. And so this is a boiling point constant. Those values will be given to you unless it's asked as the final result. Now, for freezing point, we're going to see something somewhat similar, but the difference with freezing point is you notice that it's a depression. That's why, especially up north, they put salt on the roads to depress the freezing point and get it to melt at a lower temperature. So you see here we have a difference in freezing point, a delta TF. And very similar, we still have molality. The freezing point constant, structure and functions are different, so our freezing point constant's different times I. But other than that, it simply mirrors what we saw above. So instead of molality, we put mass over molar mass, same as the other one. So it's not like you have a lot of formulas to memorize. Times now Kf times I. So those are two formulas that mirror one another. Now, what if we want to relate the boiling point of the solution and the boiling point of the solvent? The formula we have for that is that the boiling point of our solution is equal to the boiling point of our solvent. Now notice, since it's an elevation, it's plus the change. So again, there's very few differences in how these are calculated. If it's the freezing point of the solution is equal to the freezing point of the pure solvent minus, remember it's a depression, we're going to subtract that delta T. So it's going to be minus delta TF. Now, the key is, in both of these, we have a molar mass factor, and that's what we're doing in Tools of the Trade, is looking at mathematical ways to get at a molar mass. What I like to do when I work these problems is I like to lay out these formulas and then use them as a problem-solving grid to fill in my unknowns. You are past the simplistic list your givens, check your units, write your formula, plug and chug, or some people call it a guess method. We can find other ways to provide problem-solving grids. And whenever I come across these problems, if it's a boiling point, right away I set up those two formulas. If it's a freezing point, I set up those two formulas. Now, in the next video, we'll be working two of these problems. I'm going to go ahead and cut it off now so it doesn't get too long, and maybe you can process this information that we have done so far in at least getting at the conceptual aspects of these.